All right, welcome back. Today we are going to be completing part A of homework 3 for process dynamics and controls. What we're going to be doing today is we're going to take this dynamical expression for a single gravity drain tank. At this point, very familiar to us, our ADHDT is going to equal Q in minus Q out. And as we know, we're going to sub our Q out for alpha times h to the 1/2 with our alpha equal to the square root of 2g. What we're going to do with this expression today is we're going to use a Taylor expansion to linearize this so that we can perform a Laplace transform to get this into the form of the general transfer function, which I've written up here, which has a k and a tau, the k, of course, being the controller gain, and the tau being the time constant. So once we linearize this expression, as at this point it's clearly not linear, we've got dH/dt and then h to the 1/2, not a linear expression. Once we get it linearized, we can perform our Laplace transform, and then once we do that Laplace transform, we'll easily be able to get our function into this form here, from which we can solve the final problem of determining the controller gain and the time constant for any general gravity drain tank. So let's go ahead and get started with that. All right, so let's go ahead and get started with our Taylor series expansion. So the idea behind a Taylor series expansion is we're going to linearize this nonlinear function. Looking at it like this way. So we've got our h to the 1/2. Obviously a nonlinear function. What we're going to examine is our initial steady state height, which we're going to call h bar. We're going to look at its point along this curve. And then we're going to look at another point h, a height at a later time. What we're functionally going to do is try to find the slope here as to approximate this function as a line. And how we're going to do that is we're going to say that our h to the 1/2 is pretty much our h bar value to the 1/2 plus our derivative of our h to the 1/2 with respect to h evaluated at our h equals h bar all times our h minus our h bar. And this little part here, this h minus h bar, is going to be very important for finding, linearizing this. And this is actually going to be our deviation variable, which we're going to call h prime. I'm going to end up subbing this into the equation in just a second here. So moving on from here, we can also say that dh prime dt is going to equal dh dt minus our h prime evaluated at 0, which we know later we're going to be able to get rid of by plugging it in to this greater function up here. So we can say that a dh dt, dh prime dt I should say, is going to equal q in prime minus alpha times plugging in our approximation up here along with this assumption here, our h bar to the 1/2 plus dh to the 1/2 dh evaluated again at h equals to h bar times h prime as subbed in up here, all minus h bar to the 1/2. As you can see, as we set up here, these two are going to cancel, leaving us an overall expression a dh prime dt equals q in prime minus alpha times dh to the 1/2 dh evaluated at h equals to h prime times h prime. What we're finally going to do to simplify this down just a little bit more so it's nice and easy for us to perform our Laplace transform, so we're going to take this entire section right here, and since it is constant, we're just going to call this r, leaving us the final linearized function a dh prime dt equals qn prime minus rh prime. And this is clearly a linear function. What we're going to do next is we're going to perform our Laplace transform on this function to try to get it into this form up here so that we can find both our controller gain and our time constant tau for this expression here. So I'll go ahead and erase all this, give us a little bit more room, and then we can move on to do our Laplace transform. Now that we've got our linearized function, we can go ahead and take our Laplace transform so that we can get our equation into this general transfer function form. So, getting started here, we will recall that the Laplace transform of a function dy dt generally is going to give us our s times big Y minus our y prime evaluated at 0. Applying this to our function here, we can get the Laplace transform of a dh prime dt. It's going to equal our a times r sh minus h prime at 0, already evaluated as 0, going to equal our big Qn minus our RH. Now if we rearrange this a little bit and get rid of all of our zeroed values, we get a times sh plus RH. If we add this over to the other side and get rid of our h's on the same side, it's going to equal big Q in. Then solving this out for h, pulling our h out, dividing it out, we can get that our big H is going to equal Qn over a s plus r. And you'll notice this looks very similar to our general transfer function up here. But we've got our Qn and our r where our 1 should be. It's caused a little bit of trouble. So we're going to rearrange this a little bit to get it exactly into this form. So we can say that h is going to equal Qn times 1 over r times as over r plus 1. And rearranging this even farther to make this even more blatant, we can get as Qn times 1 over r over as over r plus 1. And as you can see here, now we found our k and our tau, our controller gain. And going off of this expression, match with the form of this expression, we can see that our controller gain k is going to equal 1 over r, our time constant tau, must equal a over r. Keeping in mind that way back when we said that our r is equal to r alpha times d h to the 1/2 dh evaluated h equals h r. Meaning that This is our transfer function, and these are our controller gain and time constant values once we arrange our transfer function to be in the form of the general transfer function to find those two values. So, I believe that's the end of part A for homework 3 for process dynamics and controls. All right, while I was reviewing the footage, I noticed that up here I said the general Laplace transform of a function dy dt is sy minus y prime 0. That's obviously not true. It's not y prime. I just saw in my head because of the h prime up here, but it is just sy minus y evaluated at 0. So just a little correction for the work in there. But this is the end of the video for part A of homework 3 for process dynamics controls.